Good morning, everyone. So we're going to get started. This morning we're going to have two half-hour sessions. And our first speaker is going to be Petar Simidzija, who is coming from University of Waterloo and talking to us about classical gravity and the ultraviolet catastrophe.
Thank you very much. So I want to thank the organizers, first of all, for letting me speak here in place of Achim Kemp, who couldn't make it. This is a work that I've done as a master's student with my supervisor, Eduardo, as well as Achim. And I'm going to tell you why classical gravity is safe from an ultraviolet catastrophe. Let me start with some historical motivation by talking about the theory of electromagnetism in the year 1899. So in the late 1800s, electromagnetism was a very successful theory. It could make a lot of successful predictions. It could predict the deflection of a compass needle in a lightning storm. It could predict the attraction and repulsion of pith balls. It could predict the precession of charged particles in an electric coil. And it could even predict the finite speed of light. This was years before special relativity was understood. However, despite all of these successful predictions, electromagnetism in 1899 had a serious problem. Namely, it failed to predict the outcomes of thermal experiments. So as we know, and as was known at the time, hot objects radiate light. And experiments showed a finite total radiation from a hot object. So the radiation spectrum looks something like this, and when you integrate over all wavelengths, you get a finite total radiation. However, electromagnetic theory in the late 1800s predicted an infinite total amount of radiation radiated by a hot body. And this discrepancy between theory and experiments came to be known as the ultraviolet catastrophe. So let's try to understand what caused the electromagnetic UV catastrophe. Let's consider a cavity filled with classical electromagnetic radiation at some temperature T. Then we know that there's an infinite number of modes of the electromagnetic field that can fill that cavity. That's because we can have arbitrarily small wavelength modes, arbitrarily ultraviolet modes. So we can fit in infinitely many standing waves inside the box. We also know that if we're assuming classical electromagnetic radiation, then each mode has a continuum of possible energies, and in thermal equilibrium, the average energy for each mode is going to be roughly kBT. This is just a classical equipartition theorem, which says that in thermal equilibrium, energy is equally partitioned between all the classical degrees of freedom of the system. And so then we see that an infinite number of modes times a kBT amount of energy per mode gives an infinite total energy in a finite volume. And this is what the ultraviolet catastrophe is. The ultraviolet catastrophe was solved in the year 1900 by Planck. And the solution starts by making the revolutionary assumption that the allowed energies for each of the modes weren't continuous, but rather are discrete in units proportional to the frequency. So the low frequency modes have small energy gaps between the allowed energy levels, and the high frequency modes have a large energy gap. What this does is it ensures that in thermal equilibrium, modes with a high frequency, so modes where the frequency is much higher than the temperature, can't get excited by a kBT amount of energy because the energy gap is too large. And so the high frequency modes have effectively zero energy. And when we integrate over all the modes to get the total energy in a cavity, we get a finite value. And this agreed with experiments. So this was the revolutionary insight that Planck did to fix the ultraviolet catastrophe for electromagnetism. And the main assumption that goes into this is that the electromagnetic field is quantized. Okay? So now let's fast forward to the year 2019. And let's notice some interesting insights between the theories of electromagnetism and gravity. The theory of electromagnetism describes the motion of charged objects. The theory of gravity describes the motion of massive objects. In electromagnetism, oscillating charges produce electromagnetic waves through the electromagnetic wave equation. And in the theory of gravity, oscillating masses produce gravitational waves through the gravitational wave equation. This is just a linearized Einstein equation, where h mu nu is a perturbation to the background metric of spacetime. And t mu nu is the source of matter and energy that's sourcing the gravitational waves. As we just discussed in electromagnetism, if we assume a classical theory, we're led to an ultraviolet catastrophe, which means that we have to quantize the electromagnetic field. And so now the interesting and obvious question becomes, what happens in gravity? If we assume classical gravity, do we get a UV catastrophe? And if so, does this mean that we need to quantize the gravitational field? So these are the questions that I'm going to try to answer in the remainder of this talk. So we'll consider this setup. We know that thermal fluctuations of any hot object should emit gravitational waves. Why? Because if we have oscillating energetic degrees of freedom, we expect that that's going to source gravitational waves just by the gravitational wave equation. So we have some examples of thermal objects in the universe. We know that the cosmic microwave background is a thermal object at roughly 2.7 Kelvin that exists everywhere in the universe. So we expect that the CMB should lose thermal energy into gravitational waves. Another example is stars, which in our galaxy can reach temperatures as high as 40,000 Kelvin. They're somewhat thermal objects, and we expect that they should lose energy into gravitational waves as well. However, what's important to note is that neither of these effects have been observed yet, and so they must be very small. And so then the question becomes, what does the theory predict? Does the theory also predict a very small amount of energy radiated? If it doesn't, then we would have an ultraviolet catastrophe, a disagreement between theory and observations. So our goal now is to compute, theoretically, the amount of thermal radiation radiated by a thermal object into gravitational waves. So we'll consider this setup. We consider a thermal object in some finite volume V emitting gravitational waves out to a distance r. It's well known in the gravitational wave literature, and I'm not going to get into the details of this, but it can be shown that the stress energy carried by a gravitational wave can be written in terms of the derivatives of the metric perturbation h. So we're going to use this expression to write down the power radiated by the thermal source into gravitational waves. So this is the expression for the radiated power. It's the energy divided by the time. And you see we can write that in terms of the T00 component of the gravitational wave stress tensor. T00 component because that's the energy density. Okay, now we want a more useful expression than that. So we're going to insert the T00 component into that equation. And then we use the gravitational wave equation to write h in terms of capital T, where remember capital T is the stress energy of the source, of the thermal source. Okay, so this is a more useful expression that we can now try to compute and get a theoretical answer for how much power is radiated away.
Sorry, if you don't want questions.
No, go ahead. This is great.
Little t, is that a pseudotensor or a tensor?
So little t mu nu, I didn't want to get into the details, but it's an effective stress energy carried by gravitational waves. You can't assign a stress energy to gravitational waves in the conventional sense. You can only assign an effective stress energy that's averaged over a large enough volume that contains many wavelengths of the gravitational wave. That's an important point. Any other questions? Okay, so we're going to try to compute this quantity for the power radiated. And again, I point out that capital T is the stress energy of the thermal source. So for simplicity, we're going to model the thermal source as a quantum scalar field, and then in which case the stress energy tensor takes this familiar form. But now we have a kind of problem. T mu nu is now a quantum operator, and so then equation 1 doesn't make sense really, because the left-hand side is supposed to be a real number, whereas the right-hand side is a product of operators. So we need to somehow make sense of that. So the most obvious way to make sense of coupling a quantum object to classical gravity is to consider the formalism of semi-classical gravity, where now the gravitational waves are sourced by the expectation value of the operator T mu nu, where we take the expectation value in whatever state we're interested in for the source field. So in our case, we would take the expectation value in a thermal state. Okay, so this is the gravitational wave equation in the semi-classical formalism. And then we can repeat the procedure and get the expression for the radiated power. It's the exact same expression, except that now we have expectation values on the capital T's. Okay? And now this expression at least makes sense. The left-hand side is a real number, the right-hand side is a real number. And so we can compute it. We get something interesting, though, when we try to compute this. Remember, these expectation values are in a thermal state. we know that a thermal state is an equilibrium state, so it's a time-independent state. What that means is that the stress energy tensor in a thermal state is going to be a constant in time. Notice that we're taking a time derivative here. That's what the dot represents. When we take the time derivative of a constant, we get 0. And so we quickly see that semi-classical gravity predicts that a thermal object radiates 0 energy into gravitational waves. Okay, so this is an answer to our question, but it's not really an answer that we should be happy with. We expect this answer to be wrong, and this is because semi-classical gravity inherently neglects the quantum fluctuations of the source, because it just takes the expectation value of the source. And we know that it's going to be precisely the quantum fluctuations that are going to source gravitational waves, because it's oscillating masses that produce gravitational waves. So what we need is a formalism that is an upgrade to semi-classical gravity, and which takes into account quantum fluctuations of the source. This formalism exists, and it's been studied a lot. It's called passive quantum gravity. So passive quantum gravity accounts for quantum fluctuations of the source by replacing the product of expectation values of the stress tensor with the expectation value of the product. So now the expression for the radiated power is the same expression, except that the expectation value is taken on the outside of the stress tensors. And now we can, again, proceed to compute this quantity, and a priori, there's no reason to think that this should be 0 now, and so we can try to compute it. And that's what we're going to do next. Now, before I get into computing this quantity, I just want to point out something important. In the theory of passive quantum gravity, matter is quantum. That's because we're considering a quantum stress energy tensor for the matter fields. And so this quantum matter is going to induce passive fluctuations on the gravitational field h mu nu. However, the gravitational field itself is completely classical. We're not quantizing the gravitational field. So there are no active fluctuations of h mu nu, there are only passive fluctuations. This is the reason that this theory is called passive quantum gravity, although I would argue that that's not really an appropriate name, because gravity is completely classical in this formalism, okay? So that's something that it's important to keep in mind here. We're considering a theory of classical gravity coupled to quantum matter, where the matter induces fluctuations of the gravitational field, okay? Now let's try to compute this quantity. That's our goal for the rest of the talk. As soon as we try to compute this quantity, though, we see a big problem, namely that there's divergence is present when we try to compute the expectation value of a product of stress tensors. And so in order to get a meaningful result, we first have to regularize these divergences that occur because of this. Okay? So now let's talk a little bit about the regularization procedure. This is a standard regularization procedure that's applied in the theory of passive quantum gravity. The first step is to write the stress tensor in terms of the field using the familiar expression. Plug that into our expression for dE dt, and we get something that schematically looks like this, where now we have two types of expectation values appearing of a product of fields. First of all, with the subscript 0 in red, are expectation values with respect to the vacuum state. And these terms are divergent when the two fields inside the expectation value are evaluated at the same point. On the other hand, we have the green terms, which are expectation values in a thermal state, where these are defined with the vacuum divergences taken out. And so these are completely finite terms, even in the coincidence limit. So our goal now is to somehow regularize the divergences in the vacuum terms in order to get a meaningful result. We can do this in two steps. The first step is pretty straightforward and I would say uncontroversial. Since we only care about dE dt relative to the vacuum, we can subtract off the purely vacuum terms. So then we get an expression that looks like this. This is completely analogous to subtracting the vacuum expectation value in order to compute the energy density in an excited state of a field, okay? We only care about energy differences, so we can subtract off a constant offset, all right? But even after doing this, we still have divergences present in that first mixed term. And we can't simply subtract those divergences away because this term is now dependent on the temperature. It's state dependent. So if we subtracted it off, it wouldn't be amounting to simply shifting the offset of energy. So now we need a more clever way to regularize these divergences. And fortunately, in the theory of passive quantum gravity, there's a way to do this. So to understand this, let's look at the divergences a bit more carefully. So the divergent term, the red one, the vacuum term, it has a divergence as 1 over x minus x prime to the power of n. So as you can see in the coincidence limit, when the 2 points x and x prime are the same, we get a divergence of a 1 over x to the n type. The nice thing about the green term is not only is it finite, but it also decays rapidly to 0 when the 2 points x and x prime are much larger than the scale set by the temperature. So this is going to be useful in regularizing this expression. So basically, the expression that we're trying to regularize, the integral that we're trying to regularize, looks something like this simplified integral of f of x over x to the n, where f of x is a function that decays to 0 when x is much larger than the inverse temperature. This is what kind of expression we're trying to regularize. You see, if n is 1, then we can just use the Cauchy principal value prescription to regularize this integral. However, in general, in expressions of the above form, n is going to be bigger than 1, so we have a higher order pole divergence that we need to regulate. And we can't just use the simple principal value prescription. Instead, what is done is a generalized principal value prescription is used that can regulate higher order pole divergences. And this is actually kind of, I think this is kind of interesting. The way that the generalized principal value prescription works is you write 1 over x to the n in terms of the derivatives of a logarithm. So this is an identity that you can prove very easily just by taking the derivatives of the log. And then by substituting this expression into the integral and performing multiple integrations by parts, we find that the divergent integral turns into something like this, where now we only have a logarithmic divergence appearing in the integral. A logarithmic divergence is completely integrable, so we can integrate this right-hand side and we get a finite number. And so this allows us to regularize these persistent divergences that occur in our expression. And then it allows us to compute the thermal radiation radiated by a thermal source into gravitational waves. Okay? So following regularization, we find the following expression for dE dt after reinserting all the fundamental constants. This is the expression that we were after. And now we have to ask, how does this compare to observations? We have to compare the theory to the observations. So once again, reiterating, we computed dE dt. We also know, this is a very standard result, that the energy density of a thermal state of a scalar field is given by this expression. And so by dividing these two expressions, we can find the time that it takes for a thermal source to radiate a small fraction delta of its energy. This is really the quantity that we're going to be comparing with observations. Okay? Let's do a consistency check, though, first on the quantity. We see that the radiation time decreases with g. This makes sense, because if the coupling between matter and gravity is stronger, the matter is going to radiate gravitational waves faster, and that's going to decrease the radiation time. We see that the radiation time increases with h bar. This also makes sense. If we increase h bar, that means that we have a more quantum source, more quantum, in quotes. A more quantum thermal source, we know, has its energy predominantly stored in lower frequency modes. Now, lower frequency modes oscillate slower, and so they're going to radiate gravitational waves slower, and so the radiation time is going to increase. Finally, the radiation time decreases with the temperature, and this makes sense. If we increase the temperature, the source is going to fluctuate more. The degrees of freedom in the source are going to fluctuate more wildly. They're going to emit gravitational waves at a faster rate. The radiation time is going to decrease. Okay? So this expression makes sense, at least from this, just from checking the consistency with the units. And now let's compare it to observations. So first, let's consider the CMB. Remember, CMB is an example of a thermal object that exists in the universe. Our observation is that the CMB temperature is roughly 2.7 Kelvin with a relative uncertainty of 2 parts in 10,000. our theory allows us to compute how long it would take for the CMB to emit that small fraction of its energy. So we have to compute this quantity and compare it to the fact that we haven't observed that the CMB is emitting gravitational waves. And what we find is that it would take more than 10 to the 20 years for the CMB to radiate away a small fraction delta of its energy. 10 to the 20 years is much larger than the present age of the universe, and so the theory predicts that this should be an unobservable effect. And indeed, we haven't observed it. So the theory agrees with the observations. So at least from the perspective of the CMB, classical gravity agrees with thermal observations. Let's do the same thing now for a star. It's another example of a thermal object. Our observation is that there are stars in our galaxy with temperatures of about 40,000 Kelvin. And we find that these stars have roughly time-independent emission spectra. They don't change over the years. Our theory can predict how long it would take for a star to emit enough gravitational waves so that the temperature decreases enough for its emission spectrum to change by an observable amount. However, we find that it would take more than 10 to the 29 years for the star to emit enough gravitational waves in order for its spectrum to change by a tiny 0.1%. Again, 10 to the 29 years is way more than the present age of our universe, so this is something that we would never be able to observe. Again, the theory agrees with the observations, and so from the perspective of stars in our galaxy, we can conclude that classical gravity is consistent with thermodynamic observations. Okay, and let me just conclude now. We computed the emission rate of a thermal object into classical gravitational waves. What we found is that for the cosmic microwave background and for hot stars in our galaxy, the theory completely agrees with observation. So there is no gravitational ultraviolet catastrophe. And the conclusion that you can take away from this is that if gravity does need to be quantized, it's not going to be because of the thermal ultraviolet catastrophe. This is in contrast to the quantization of electromagnetism. Thank you.
All right, so we have about 10 minutes for questions. I see Chris.
So I guess I'll go first. So I'm just curious, so this is really interesting work. I'm curious if there's a way in which the methods you're using could approach a more general question, which is, are there any systems that radiate gravitational waves such that there would be a UV catastrophe? So I'm asking this partly because it seems like the linearized assumption is a strong one here, and if you're looking at, other types of systems like black hole binaries that lead to gravitational waves, and I assume you're not in that case using linearized field equations. So, I mean, it's a very different question, but I'm curious whether
right. So,
approach it more general.
Well, definitely, we all know we've observed gravitational waves from black holes.
Yeah.
It hasn't been catastrophic, but remember, our perspective here is to had the motivation that we want to compute the gravitational waves radiated by a thermal source.
Yeah, no,
because it's exactly the thermal properties that gave rise to the electromagnetic UV catastrophe.
Right. But the question is there a different kind of UV catastrophe which would just be a source of radiation that leads to the sort of infinite energy radiated, even if it's not a thermal source, if it's some other source?
Right, I'm not aware of it, but if there existed something like that, and if the theory predicted a catastrophe, that would clearly be a problem, and we would need to somehow fix the theory. But I'm not aware of anything like that.
Yeah, so I wonder if this interpretation of the UV catastrophe is inconsistency in classical electrodynamics. If this is the only interpretation, alternatively, maybe I could think that maybe there's something wrong with the assumption of thermality there in those modes. If I imagine, for example, a gas of charged particles is my model for a black body, then this would radiate some things in classical electrodynamics, but there would be energy conservation, right?
Yes, exactly. And the observations show that there is energy conservation. There's a finite amount of energy radiated by that hot body. That's exactly the problem with the classical electrodynamics, because if we do a naive theoretical calculation, where we assume that the electromagnetic field is classical, we get completely unreasonable result that there's an infinite amount of energy radiated.
No, but the question is what is wrong with that calculation? It could be wrong that there's classical electrodynamics is inconsistent in some sense, or it could be that the assumption of thermality is wrong.
I see. That's a good point. That's a good point. But the way that I think about that is, if we have a hot gas, I can stick a thermometer in there and I can see that it's a thermal state. So the question of thermality seems to be correct. That gas has thermalized and it's in a thermal state.
But if you take those infinitely many modes, those are an extremely large system. And typically, if you look at how thermality and thermal states are derived, it uses that your system is much smaller in the bath that it's immersed in, right?
Yes.
So I feel like there may be some skepticism.
I think I agree with you. I think there might be. But nevertheless, the naive calculation does lead to the ultraviolet catastrophe, which does lead to the conclusion that the electromagnetic field is quantized, which we seem to think nowadays is the correct interpretation. So it was our hope that even despite all of these nuances, if we could get a naive calculation like that for gravity, maybe we could come to the same conclusion. So I agree that there are definitely details there that are not so obvious.
Wait.
Actually, this is good because what I was about to say follows up with what I was saying. So something's going on here that I don't understand, and actually, one way to explain it connects to the classical electromagnetism. So the classical ultraviolet catastrophe, it's not just electromagnetism, it's electromagnetism plus equipartition, and that presupposes you've got matter in thermal equilibrium with the radiation bath.
Yes.
And actually, historically, one response, and this was serious, people were taking this seriously well into the teens, where it was that to say, well, perhaps matter equilibrates very slowly with the radiation bath, and so if we let things sit long enough, eventually they would radiate all of their energy into electromagnetism, but the systems we're actually seeing are not in thermal equilibrium. And the reason this connects with, because you wouldn't, from thermal considerations alone, you would only expect to be able to calculate the equilibrium properties, and not the rate at which equilibration happens.
That's right.
So this is what puzzles me. So let's bring it up to your calculation. Could you go back to your theory? You seem to have got So guess that there. You seem to have gotten from thermal considerations alone something to do with the rate at which something is going to equilibrate. More or less, something that's independent of the nature of the system. And this is puzzling me because if I think about how fast things are going to emit energy by gravitational waves, well, if I've got gas of little tiny particles, then mass distribution is to a high degree of approximation almost totally uniform all the time, and it was very little gravitational radiation. But if I had a whole bunch of really massive things moving around like crazy, I would expect a lot more gravitational radiation. So how can I get kind of a rate of radiation that's independent of the system?
That's a really good question. Two really good questions. The first question that I understood was, we're using thermodynamics to predict a rate, which would seem to imply a non-equilibrium process.
Right.
The important thing to keep in mind there is that this is the rate that it takes the thermal object to radiate a very tiny amount of its energy. So we're considering a process that's very close to equilibrium. That's why in the previous slide, I said that this expression is valid when delta is very small. Delta is a small fraction of the energy radiated away. This is, I think, a meaningful expression then, because we can consider a thermal object. We know that that thermal object is radiating away energy. We can compute how much time it takes for that thermal object to radiate, let's say, 1% of its energy. We're not working out of equilibrium there because 1% is a very small amount of energy. That's my explanation for how we can compute a rate, even though it seemingly might not appear to be correct.
We have
But
minutes and people left. So.
he has a very good second question. Could I answer that as well? The second question was, this seems like a universal expression that applies to any source system. It's not. I consider it a scalar field. So this is an expression that applies to a scalar field, a massless scalar field. The reason that we consider it a massless scalar field is first for simplicity. Second of all, because it's a very good approximation to the CMB. You might say it's not a good approximation for a hot star, and I completely agree with that. But we still expect that up to numerical prefactors of order 1, it should probably give a correct answer to a hot star. Although we agree that if we considered massive charged particles, there would be a larger fluctuations in the energy density, and so we might expect more gravitational waves to be emitted, and that's something that we're looking at the moment. But this expression is valid for a massless scalar field only. Okay.
So Ben, I have like a 1-minute question.
Yeah. So really quickly, I was just wondering, because you use this passive quantum gravity framework, why is that framework appropriate, and are there approximations involved in that as well, like kind of piggybacking on the previous question?
Right. So this framework we came up with kind of independently from the previous work, because we tried to come up with a method that generalizes semi-classical gravity to include quantum fluctuations. Remember, the problem with semi-classical gravity was that it didn't allow for quantum fluctuations. And then we realized that this framework was actually used by mainly Larry Ford and his collaborators over the course of the last 2 decades to study a lot of different phenomena where you want to compute how stress energy fluctuations affect the gravitational field. And it's been used even to compute fluctuations in Casimir forces, things like that. And it gave predictions in those contexts that make sense with observations. So from that perspective, at least, we're happy with the formalism. The assumptions that go into the formalism are the same assumptions that go into semi-classical gravity, except that you're slightly more general in that you're allowing quantum fluctuations. I'm not sure if you have.
So unfortunately, we're out of time. I have a number of people still on the list, so please make note of your questions because we're going to have a panel discussion again later, so that would be a good time to ask questions that didn't get asked now. So let's thank Peter again.